Great, thank you. Yeah, thanks for not telling anybody exactly how many years I've been here. I realized the other day that I am teaching people that weren't born when I started at WPI, so that sort of gives it away. I tried to imagine what that would be like when I was in college. All right, introduction to axiomatic design and as a scientific discipline. Let's start off with why we want to do it. You know, people say better, faster, and cheaper. You know, pick any two. If you're good, you can get all three. And what we're trying to, one of the things we do with axiomatic design is we remove non-productive iterations, and I'll show you how this is going to go. We reduce the complexity. And so among other things, we provide metrics. How do you tell if a design is going well, and how early in the design can you tell? Communicate the design intent. This is done so poorly most of the time. We could build another Saturn V moon rocket. We've got the plans, but we couldn't change it because we don't know why those things are there. The design intent was never properly recorded, and that's not unusual in industry. And then how do you know that you are selecting the best design options? And controlling costs, these unintended consequences. The poor 787, so many ways a beautiful aircraft, and you know, so can we avoid that kind of thing? One of the reasons I'm doing this is sort of to advertise the conference that we're going to have at the end of June. And so this is the 7th International Conference on Axiomatic Design, and that's Nam Suh up there, the father of axiomatic design. He worked on that when he was at MIT back in the 70s, and I got introduced to it when I was a graduate student. He came to the University of Vermont where I was. Anyway, so we'll need student volunteers for this, and there's opportunities to present posters and case studies. If any of you have been using this, like in my class, MFE 520, ME 5, whatever it is, 543. So we welcome that, and the abstracts aren't due for another couple of months. Let's see, believe it or not, that picture's from Worcester. Can anybody tell where that is? Institute Park. There you go. Our own Institute Park. All right. So one of the things, you know, and I think in Massachusetts there's some bias because we've got, you know, this big Boston Museum of Science. In Paris they have Engineering of Science or Museum of Science and Technology or Science and Engineering or something, but we get hung up on the science, right? And we talk about rocket science. It's actually rocket engineering, and this is where it came from. So anyway, so scientists look at things as they are and ask why. Why is the moon up there and keeps going around the way it does? But engineers dream of going there and ask, why not? So what we do as engineers is we design. That's dreaming of things that never were and asking, why not? But when we say, is engineering, design, and art or science, some people start getting sort of attached to this. But let's take a look. A scientific discipline, as opposed to like scientific process or a science, a scientific discipline is one where we've got a few simple, compact, sort of self-consistent laws that we can use to solve a wide variety of problems. Now, art is sort of cultural, subjective, experiential, emotional, and people want it to be that way. And both things can be beautiful. So I'm not putting the art down, but as engineers, what would we rather be teaching? All right, so supposing that design is not a science, right? So it's difficult to measure progress. You rely on subjective evaluation of quality, difficult to teach, rely heavily on experience, difficult to predict the outcomes. But I think this is true of a lot of ways we do design. Actually, an interesting question that I ask my MQP students as we're working on this, I'm saying, and I'm trying to convince them out of using axiomatic design. I say, so what are you doing now in design, in your design method, that you could not have done 4 years ago? And so what is it that you've learned here at WPI that's actually helping you with the design process? All right, so there's a lot of analysis we've learned, but actually organizing and telling if it's a good design. But it's not just WPI seniors that are like that. I go out into industry and talk about this and go, how can you tell if this is a good design concept right from the beginning? And that will do a lot to help you reduce costs and get products to market faster. Two things that are also important for MQPs, right? So, so if we're going to have some axioms or rules or laws, like I'm talking about, to make design a scientific discipline, one of the key things when we think about it is they need to address change. And mostly we haven't thought about this very much. And I have to confess, I've been using axiomatic design since I was in graduate school. And it just occurred to me a couple of years ago, geez, this change is what we're looking at, right? And people say the only thing that's constant is change. And so, well, one thing we're doing, I mean, if we don't want to change anything, we don't want to do anything differently, maybe we don't need to do any design. So change is, or design is about fulfilling functions, doing something differently, or adapting to change. I suppose we say, well, I don't want anything to change, then you still have to design something to keep it from changing because everything else is changing. So we need to create change, we want robustness in the face of change, and we need to be able to accommodate the change somehow through adjustability and controllability. So this gives us some ideas of what we want to do. Engineering design, though, is everywhere. I mean, just when you're planning, you're doing some sort of design problem. In fact, I was bold enough to say at the 5th International Conference on Axiomatic Design that any problem can be stated as an engineering design problem. And since axiomatic design is the best way to address engineering design problems, and axiomatic design is the best way to solve any problem, so I did that in a very safe environment, but now I'm trying it out on you guys. One of the things, too, about engineering design is that it's top-down. You know, we start with, geez, we have a problem we'd like to solve, and then it's functionally based. We want, you know, we're trying to achieve certain objectives. And here's something I'd like to digress just for a moment on, because this fits pretty well if we think about it. Design, we're creating value by thinking, right? I mean, this is the nice thing we get to do as engineers. We make little sketches, draw some things, a computer program, then we pass it off to somebody else who has to do the machining. Now here, with the MQPs, we get the students to do the machining because we can't afford enough machinists, but it's good for you to learn about it anyway, right? But for the most part, the engineer does the design, which isn't useful until you actually make the thing, right? So we're creating value by thinking. So if we're doing that, we ought to think about what thought is, right? So thought is about semantics. And actually, this guy, Eric Baum, wrote a book, What is Thought? And what is semantics? Well, we're trying to capture somehow and exploit the compact nature of the world, like in physics, right? So when Newton says F equals ma, boom, a whole bunch of problems can be addressable with that fundamental equation. So we've got a short list of laws that can predict many phenomena. Apples falling on the earth, planets going around the sun. So what do we have for design? And this is one of the things that Nam Suh was asking. You know, so we've got laws for thermodynamics, laws for mechanics, and certainly I think when Newton started saying, well, there might be some fundamental laws for mechanics, I bet there were a lot of people. I was very young at the time, right? But no, I haven't been at WPI that long. I'm sure there are a lot of people who are saying, no, there's no laws for mechanics. Mechanics is experiential, right? You know, I've been building these water wheel thing or whatever, and then, oh, if you haven't built this, well, you can't possibly do this, or you can't solve these problems. But now, yeah, if you know F equals ma, there's a whole bunch of problems you can solve without actually having experienced them. So we've got this short list of rules. We've got the semantics. And so the challenging thing is, can we figure out what these are and apply some short list of rules for engineering design? All right, so semantics. So thought is about semantics, right? Because when we think of something, it's not the physical thing. It's some connections in our brain, and maybe we can reduce it to some sort of symbols. But when I think about a chair, it's not a chair inside my head. It's some representation of it. And so then we get, you know, syntax, and how can we put all these things together, just like in mathematics, right? And so can we develop some appropriate symbolic representation for the designs that will be useful in seeing if we're actually designing things. That's what I'm going to be showing you. So once we get a symbolic representation for the design, then can we somehow manipulate these symbols and achieve the best design? And that's what we're talking about. So if we look at the state of the art, so one thing when I tell and I ask people in my class, I say, all right, so how do you tell if you have a good design, right? And then there's a bunch of things, well, it completes the functional requirements, or does what it's supposed to. Okay, right. It doesn't cost too much, right? Okay. But if you have two designs that are the same in terms of they both fulfill the functions, they both have the same cost, then how do we tell which one we pick? And well, sometimes you get down to the KISS. Keep it simple, stupid. Now, is that good enough as an axiom by itself? So is it self-consistent? And here's, I think, the more important one, and it's not really self-consistent, because is the application of this simplicity, say, axiom, simple? So let's say your job is to select the next, I don't know, car, drone, attack aircraft, whatever, aircraft carrier. How are you going to tell which one's simpler? Because these are very intricate, sort of complex things. The next online electric vehicle or mobile harbor, which are two things that Nam Suh has developed in a very short time in an academic environment, and he'll be talking about that at his keynote. Anyway, so essentially we can think of these two axioms as being a decomposition of simplicity. And so, in the thing that sets axiomatic design apart, and although some of my students, and it's probably my fault, get this confused, they think more of the process and the decomposition that we're going to see. But the fundamental thing in axiomatic design is what? Axioms. So here they are. The best designs, and this was Suh's premise, that if we have the right axioms, we can select the best designs. So the best designs maximize the independence of the functional elements. So this makes a design controllable and avoids unintended consequences. Right? So we're talking about change, and so as things change, how do I control it? I don't like unintended consequences, so what would be the alternative? Let's have a design with lots of unintended consequences and it's completely uncontrollable. All right. And so then minimize the information content. I think it's a little bit confusing because people are, I like information, right? This is information content more in the sense of Shannon or in the sense of Boltzmann statistical thermodynamics. And so what we're trying to do is maximize the chance of success. And this makes the design more robust, and it's based on probability. So we'll take a look at both of these things in more detail. But where does this come from? Well, whoops, and I didn't update this slide. So Nam was at MIT when I was a grad student, and he was nice enough to come up to Vermont where I was studying and told us about what he was doing in about 1980. And when I finished my doctorate and went to work in Europe, I sort of took those ideas with me and started using them in industry. And I thought, this stuff works pretty well. And because the only kind of courses we'd had on design were algorithmic, and I'll talk about that in a moment. So Nam just retired as president of KAIST, which is the Korean Advanced Institute for Science and Technology. And that's a fantastic place. If you ever get a chance to visit, you should go. It's an amazing school. And it's neat. Back in, I think in the 80s, he got an honorary doctorate at WPI. First of many honorary doctorates for him. Anyway, so working with a group of students, they started off on this premise that there might be some axioms for that sort of govern good designs, and that would lead to the best solutions for design problems, something all designs would have in common. He's written 3 books that address this. The first one published in 1990, and I've been using this, or extracts from this. I used it first in my grad course in WPI in 1990. When I got back from Europe and I said, hey, I'm teaching at WPI, I've got this grad course and half the people are practicing in industry. And I want this course to be more than just a kind of rite of passage where we'll see, well, all right, so how much calculus can you remember to pass this grad course? I set a goal that I said I want within, say, 2 weeks to a month at the beginning of the course, I want the people who are practicing in industry to come back and tell me, I used something I learned in this course at work already. I wanted this to be a good, solid engineering course for practicing engineers. And every year, not everybody comes back since I've used it, but I've had it every year. Some students are always coming back within the first couple of weeks or month of the course saying, yep, I've used what I learned in this course already at work. So one of the problems, and as I know with the grad students, you're going to be in a position where you've got to sort out which design you want to put resources on. And the problem is when you talk with the engineers who came up with the design, everybody wants to see sort of their design represented in the next generation, right? So designs are like babies. They always look good to the people who made them. And what we need is some sort of objective criteria, and the axioms can supply this. And so we avoid these prolonged, non-productive discussions that really come down to, I'd really like my idea or my stuff in this next design. So what we do, and I was about to put Mike Schapulski's year at WPI up here, and I couldn't find it. That's what that apostrophe is going. He got his undergraduate degree here, was an All-American baseball player, and then got master's and PhD, and he now works at Hypertherm in New Hampshire. He's got a nice blog on design. But so he was saying that axiomatic design, and this was, he went from, after he got his doctorate, he went to corporate research at GE, and said, this takes us from argument to analysis. And so we have some criteria. These are the rules of the game. And another way that I like to put it, because I end up consulting with industry and things that I know nothing about, like batteries, for example, but I know the grammar, I know the vocabulary, I can do the editing of the design. I'm like a good English teacher. I might not have the idea for the greatest novel, but I can help you write it. I can't, but I'm trying to come up with some metaphor. So it's like the grammar, and the practicing engineers in a certain discipline know the vocabulary. So state of the art. Let me get back to this for a moment. So lots of times, particularly in industry, or if we look at the books on design, what we're talking about, there's an algorithmic approach. First you do this, then you do this, and if you're in industry, get a signature on this, get somebody to sign off on this, to do this step, right? And what it assumes, essentially, is that if you have the correct process, you'll get a good result. And I think it's easy to think, yeah, I could do the correct process, maybe not, but okay. And often there's sort of iteration, trial and error. I don't know if it's going to work, let's build it and try it out. And the evaluation by experience. And whenever we have some sort of contest here with, MQP or graduate things, you need somebody with experience to understand if that's a good design or not. It would be interesting to see if you could do that without that. All right, so how does this contrast with the axiomatic approach? One, it assumes that the axioms are there. Now, axioms, keep in mind, can't be proven. Axioms can only be disproven. Right? So F equals MA. I can't sit down and write a proof for that, but we just say, well, until we get into, it's got a certain domain of applicability, and it always works there. And we haven't seen anything that says it won't. So the axioms are the same way. And one of the things I do, too, is I challenge students to say, hey, this is only 30 to 40 years old now, axiomatic design, unlike, say, Newtonian mechanics, which is more like 300 years old. So there's still a good chance maybe we'll find a violation here. Maybe we can show a design that doesn't meet the axioms. Let's try it. This is engineering. It isn't religion. All right. So it requires some decompositions, the hierarchical structures. I'll show this in a moment. And then the evaluation is by the rules and the axioms. And there's some rules that go along with the decomposition. What this allows us to do, essentially, and gets us away from the iteration, is we do functional modeling on the design from very early stages to see, is this going to work? Is it going to comply with the axioms? So in order to apply the axioms, we need a structure. Just like if we're going to apply F equals MA, we need some sort of free body diagram. And then we need some way of creating that structure, and that gets us a process. When I teach this, I decompose it this way. I say, well, we've got the axioms. Those go at the top. To apply the axioms, we need a structure. And to create the structure, we need some sort of process. And then these can each be decomposed. You've already seen the two parts of the axioms. Structures, we'll take a look at the horizontal and the vertical decomposition. In the process, first we decompose the problem until we find out what all the fundamental elements are, until the solution is obvious. And then we have to physically integrate it back into one thing. So first, decomposition, horizontal decomposition into domains. So, and you'll get a feeling for what these are in a moment as I explain them. So customer needs, or we call CNs, and there's a few things that are good to remember. And when I teach this in industry, I usually say, here's a reference sheet, an aide-memoire, so that you know what I'm talking about. So CNs are customer needs. FRs, that's an important one to remember. We'll use that again. Functional requirements. So first, what adds value? What does the customer want? Then as engineers, we need to take that and say, all right, what are the functions that we have to accomplish in order to make the customer happy? And so that they see the value in it. The next domain is the physical domain, and this has design parameters, DPs. And this is essentially, what does it look like? What's the physical solution? Now, not all the problems require a physical solution. Some of the problems may be software, right? So it's, or maybe organizational charts. So, but this is what we mean by the physical domain. So what does it look like? And then process variables, how do you make it, right? So if we're doing some sort of simultaneous engineering or concurrent engineering, we can look at these three functional, physical, and process domains concurrently. There's also constraints, and so this is another thing we need to keep in mind. What things do we have to avoid? So these may be some kinds of physical, legal, whatever limits, or things that need to come together, or things like weight and cost are constraints. So what we're going to focus on is, and the meat of the whole thing, I think, is getting between two sort of engineering domains, the functional and the physical. Now we can spend a long time trying to figure out how to get the functional requirements from the CNs, that's important, and how to make it is important. I mean, I teach manufacturing, but we can also pose the sort of the manufacturing question in terms of functional and physical domains. But so these are the two domains I want you to keep in mind for the rest of the lecture here, and FRs and DPs. So FRs, these are the functions that the design needs to fulfill in order to keep the customer happy. This defines success in the design. No design is going to be better than its FRs. If it is, in some ways you can say it's not a good design. I worked for Atlas Copco. They started to get into the home compressor market. They made excellent quality compressors. And they didn't understand what the upper limit was and the price. They, we got something even better than what the customer wants and what the cheaper ones are. And it was a complete flop. So you define the FR so that it satisfies the customer, and that's what you're trying to achieve. And so you got the FRs, that's what we're working on, and when we have got those, then we know we're successful. So the FRs are keys, providing the desired function. Now it's amazing too, and I know when I was working in industry, how often we would start off on a very expensive, hundreds of thousands of Swiss francs, design project without saying, here's the functions we're trying to fulfill. All right? So it's terribly important to know these. You got to know where you're going. If we do these things, we're done. We got it. We're successful. If you don't know where you're going, you won't know when you got there. All right. So design is about solving problems. This means changing some things. So the FRs, too, are going to be what needs to be independently adjustable. So adapting to change and capable of providing change. All right, let me give you an example. Now, this is about naval warfare from the Civil War, Monitor versus the Virginia, or if you're from New England, it's called the Merrimack. But I always wondered when they called the Monitor and the Merrimack, why did the South name one of their ships after a river in New Hampshire? But it was originally a Union ship which sunk, and the South raised it. The South was good at doing things. They made the Henley, which was the first submarine to sink a ship. And so they were pretty handy at naval warfare. Now Erickson, who did the Monitor, and that was built in New York, and actually got at sea trials on the way down to engage the Virginia. And I'll use the Virginia just in case there's somebody from south of the Mason-Dixon line here to show some respect for. Anyway, so he wasn't using axiomatic design, but we can look at these breakthroughs, and this was a clear breakthrough in naval warfare technology. And so we can see, well, if he had been using axiomatic design, how might this have looked, right? So, and this is the thing that happens. The smaller, slower, outgunned Monitor neutralizes the Virginia. How does it do that? Well, all right, so already, and you can see in the background of that depiction, there were sailboat or sailing ships there. So you could decouple, you could make locomotion independent of the wind. Now, both of them already had that, so you had the steam power. But the key on the Monitor was the swivel turret. So this decoupled or made independent direction of fire and direction the boat's going. And this turns out to be a real big advantage. So there's a new FR. And as we're looking at, how do we be creative as engineers? How can we think of the new products? All right, understanding better what the customer needs are and coming up with a new FR is a key thing. So adjust the direction of fire. So what we're trying to do, right, is address axiom 1, maximize the independence of the functional elements. Shooting cannons at the other ship is an important customer need if you're in naval warfare, right? Or getting projectiles, right? So the swivel turret. So on March 8th, actually, I didn't put this in here, the Virginia goes out into Hampton Roads and basically starts sinking Union ships at will. This is very important because the Union was doing a good job blockading the South, and they weren't able to trade with Great Britain and get the stuff that they needed to fight better. And so we were up here, like in Worcester and New England, making guns and things and trying to keep the South from getting them. It wasn't our brilliant generals in the North that won the Civil War. It was largely our manufacturing capacity and ability to keep the South from getting the equipment that they needed. So the naval blockade was very important. And so they have this, the Virginia, so it's ironclad, it's got all kinds of guns, it's got steam, it's fast. It just starts running around Hampton Roads sinking sailing ships. The Monitor arrives on the 9th, slower, badly outgunned, much lighter. And so in naval warfare, if you look at all these things, you go, I think I want to get out of here. And because if you have that kind of disadvantage. But we can see in this depiction too, the guns on the Virginia fire out to the sides or front and back. And so the Monitor has positioned himself at, and I can't tell which is the front and the back on this boat, but I don't know. So it's like 45 degrees off the starboard bow, and there's no guns pointing that way. And the Monitor can keep moving around as the Virginia tries to adjust to shoot at it and keeps firing at the Virginia. So the Virginia, while it wasn't sunk, it was neutralized. It went and hit up in a river and never came out again. This was so frustrating for the captain of the Virginia that he accused the captain of the Monitor of not being a gentleman. If you're from the South, you know what a big insult that is. If you're from Massachusetts, I didn't think I was anyway, so. All right, so what does this look like? What we do when we when we look for the coupling and test for axiom 1 is we set up a matrix and we say, well, here are the FRs, here's what we'd like to accomplish. And then up on the top we have the DPs, here's the physical way we're going to do it. So in the Virginia, to adjust the direction of travel and to adjust the direction of fire, you basically have a rudder. So this is coupled. Now on the Monitor, we've added the swivel turret. So as a first look, we could say, well, we put the turret there to adjust the direction of fire, and we've got the rudder to adjust the direction of travel. So, all right, we have an advantage. Now, is that correct? Does that look good? Did we get that one right? So what we do is we look and we say, all right, the rudder influences the direction of travel. The turret doesn't influence the direction of travel, so we'll put an O there. Where we have an interaction, we put an X. So here, yeah, we put the turret on to get this, right? This is a corollary. I'm sorry, I shouldn't have pushed. Microsoft changed the arrangement of the slide on me. They haven't understood Axiom 1 very well at Microsoft, but we're stuck with it. All right, so the rudder adjusts the direction of travel. Should this be an O or an X? X, very good. So we would like to have, when we do the design, a diagonal matrix. So each DP influences one and only one FR. That would be the best. However, is this correct? I got two. There we go. All right. So this is now corrected. And so we have the X here for adjusting the direction of the rudder also changes the direction of fire. So what this tells you, when you have a triangular matrix, you can still solve without iteration, but you need to know the right order. Right? And so with just two things is not that tough. You know, all right, I steer, I get going the way I want to go, and then I'll adjust with the turret. Right? So this says, all right, first I've got to adjust the direction of travel with the rudder. I may have done something I didn't like to the direction of fire when I did that, but now I've got the turret so I can adjust that. So there's the order of adjustment, DP1, DP2. Not too tough, but if I've got 5 or 6 DPs and FRs and they're sort of out of order, what this is essentially is using linear algebra to straighten this out and rearrange the matrix by moving columns with the DPs and rows with the FRs. You should have been exposed to that. And you can get it into a triangular form, and you can see then what the right order is. This is something, and lots of times when you have an existing system that you're analyzing, you'll see that somebody's trying to adjust it in the wrong order, and they can never quite get it adjusted because something else goes out of adjustment, right? And all you have to do is just make a little matrix, look where the X's and O's go, let's rearrange this. Here's your order of adjustment. You don't have to iterate anymore. We'll take a look at another example. But first, innovation, and we talk a lot about this. So, but we don't really get into the meat of, you know, how do you do it? How do you innovate? And I know in the business school, you know, the innovation is market penetration. As a mechanical engineer, I'd like to think innovation is some neat technological insight. But so improve the independence of the functional elements. That's one way to innovate. And then reduce the information content. So look for opportunities to do these things. And then, of course, you know, we talked about get a new FR. All right, let's take a look at another example of adjusting things. So this was the sink over in Washburn before they replaced them a while ago. But so this is the question. All right, so here's a sink with a hot and cold water. Is this a good design? What do you think? All right, you can't really tell because we don't know what the FRs are, right? These are DPs. These are physical things, the two water valves. So without knowing what the FRs are, we can't really tell if it's a good design. So we might go back to the customer needs. Suppose we want to wash our hands. So what does the customer want? Well, if I want to wash my hands, I would like water at the right temperature, and I'd like it at the right rate. So if I get the right temperature water, I don't burn my hands, not too cold, right? The soap works fine, I can clean them off. And then I get too much water or a little trickle, and right? But the problem is, if I look at this now in a traditional sort of bathroom sink and go through the little matrix, when I turn the cold water valve, it changes the temperature and the flow rate. And the same thing when I do the hot water valve. So this is what we call fully coupled. We can't make it diagonal. We're stuck with that. And this is fully coupled. And so we have to iterate to get a solution to the problem. And so, you know, if you go, you know, if it's your own sink, you know about how to adjust it. But if you go into, you know, some other place, you turn it on, oh, it's too hot, and you turn on the cold or something. Yeah, now you have a high flow rate, and it's all over me. And you iterate a little bit, and eventually you get to a solution. Now, all right, so if you're just washing your hands, playing in the water, it's not too bad. But If you're trying to make a product or you're in, a more critical kind of situation, you don't want to do those iterations. And if you're, trying to come up with the next cell phone, you don't want to be iterating, because if you're 2 weeks late coming out with a cell phone with the features, you lost a large market share. So how can we do design without doing that? And how can we avoid that? So the problem is this requires iteration to reach a desired solution, and the DPs aren't addressing the FRs individually. Every time Microsoft comes out with a new version, you copy slides over, it moves things around, all of that. And I caught some of these, I missed that one. Anyway, so maximize the independence of the functional elements. So that's the thing. All right, let's take a look at the space shuttle. We had problems with the space shuttle. We were supposed to have one LOC in 500 missions. LOC is loss of crew. When we lost the Columbia, we were up to one LOC in 50 missions. So we missed by an order of magnitude, and not on an inconsequential part of the design, by the way. Huh? So how could we possibly have foreseen that there was actually very high-level coupling in here? So was this a good design or not? Well, what were the FRs? We wanted to carry people into orbit, and we needed to carry cargo into orbit. Why use one launch vehicle for both of those? So how could they be satisfied independently? So one day, when I had figured out that I had way too many things to do and I wasn't fulfilling all the promises I'd made to get stuff done, Nam Suh calls me up and says, "We want your help on a problem." And I said, "No, I already decided I'm too busy." He goes, No, we're working on the survival system for the next orbital space plane." And I thought about it for a few minutes and decided I could make one more promise and break some different ones. So it was fun. So I got to bring some WPI student to work with us, and we were working for a NASA contractor, and it was a big deal. How do you make sure that the crew stays alive and get over this problem of one loss of crew in 50 missions? So yeah, how do you make flying on the space shuttle safer than the chance of drawing the ace of spades out of a deck of cards? So the next one actually used two different launch vehicles, and they could get together in space, and we'd already solved that problem with Gemini or Apollo, I can't remember, back in the 60s. And so the next orbital space plane, the first version of it, looked like a Subaru station wagon with wings. Much smaller, you don't need so much fuel, and so anyway, so much easier problem to solve. So the coupling here was a mistake, you could say. All right. So these were the two functional elements. They were linked in this. It was a neat machine. It was fun to see, but it was catastrophic. All right, so that was some Axiom 1. Let's take a look at Axiom 2. Now, there's so much low-hanging fruit in design that you can do all kinds of things with Axiom 1. If that's all you ever use, that's great. A few years ago, when I started writing papers on how I was teaching axiomatic design, I tried to get in touch with students who had been in my class and had taken it. And I said, are you still using it? Or, what have you done? And I got a patent based on this. We saved the Navy $200,000 because I recognized the Axiom 1 situation. They're just using it qualitatively. And I thought that's pretty neat. That's pretty exciting because I can't even remember some of the courses that I took, let alone can I remember an instance where I used something from that course. All right, so let's take a quick look at Axiom 2. Axiom 2 is about robustness, sort of design for Six Sigma kinds of things, and how do we do that? And so what we're really trying to do is say, how do we maximize the probability of success? Now, both of these have mathematical components that you can't get into in an introductory lecture. So, we're looking at how about uncertainty. Can we hold this tolerance, for example? Will I get these things delivered on time? How can I minimize the impact of things that might be difficult to foresee, like weather? And so robust design. And sometimes you have just a one FR design, and then the whole thing is about selecting based on axiom 2. So I made this little thing up. I had a neighbor that came to me with this problem. He was designing a chair, and it was a special kind of chair to fit your anatomy just right or something. And he needed some adjustment things, right? So he said, well, how should I design the spring? I want a little lever where I put it, put it up, I can adjust something, and I put it down, and it stays where it is. And so I said, all right, well, what we have, we want to squeeze these two things together. And so this little piece here is acting like a spring. And the question is then, do we want a real stiff spring on that so that a little bit of movement in the lever comes in really forcefully, or would I like a softer spring in that? So here's my equation. So the FR is to provide a certain clamping force, and the X is the displacement of the spring, and the K is the stiffness. So which do we want? Stiff spring or soft spring? All right, I won't make you raise your hands to do this, but now, and I'll confess something too. When I first saw this problem, I chose wrong. So if we look at this graphically, and we plot the FR versus the DP, right? And so here's the spring constant. K1 is a stiff spring. Here's the FR with its tolerance, right? Because you can't have too big a force, you break something. Too small a force, they'll slip. So, and then if I take the stiff spring, all right, so what, with a stiff spring, what kind of physical tolerance does that give me? So I'm going from a functional tolerance now to a physical tolerance. What kind of physical tolerance do I get there? And now I can compare that with the softer spring. And you can see with the softer spring, I get a much bigger physical tolerance. So I'll be able to accept more variation in manufacturing, as the joint wears, as temperature changes. The one with a softer spring will keep functioning. When I go into industry and I say, have you had design for Six Sigma? They go, yeah, the importance of having as big a target as you can. They ever tell you how to design things for this? No, we're all talking about design for Six Sigma, but actually how do I do the design so that it helps? They go, well, here's one. Use the softest spring. Now, there's a lot of things that have got this kind of relationship, so it doesn't apply just to springs. So softer spring, bigger the design range, right? Now, there are some constraints, because the softer the spring, the more space you need and things too. So allow for variance. I already talked about that. Accommodates impacts. Okay. And one of the neat things is that I can take, because it's mathematically, I can figure out what the information is, because it's equal to the log of 1 over the probability of success. So everything's got the same units, so depending upon what kind of log I use. They're all bits or nats. So, is somebody going to be able to deliver this on time? Can I make it? How do I do it? So I can put all of these things into one problem, and they all have the same units. So I can compare, should I make it myself? I'm not very good at it, so my yield might be low, or should I get it made in Chicago and get it flown in? So all tied in. So what we're talking about, and getting into some summary things, I'll show you one more example. So what we're looking at is trying to be successful in the design. We define the success with the FRs, and we know that a coupled design has a lower chance of being successful. And then after we get rid of the coupling, then we go, all right, now let's just take a look at pure probability of success. The coupled design obviously is a lower chance of success. So maximize the independence of the functional elements. I was saying that's probably the most important thing. Let's take a look at the decomposition too, very quickly. How do you get a good decomposition to do this? And it's top down, and so at the top level, we're looking at the whole design, but we don't know how it's broken apart yet. So here's some things about how it gets decomposed, and you can have a hierarchy in the decomposition. And so what we're doing, and you can see, we have the equation, and we see, well, here's an FR. Is this a good DP to satisfy it or not? And we go back and forth between the FRs and the DPs, getting more and more detail. So at the upper level, we might not know if we're using a mechanical system or a pneumatic system or a hydraulic system or electromechanical. And as we break it down, we keep trying to decompose it and select DPs so that we maximize independence. One of the things, if we look at this, how to decompose, there's certain rules that work with decomposition. We should really study these, and we don't very well. There are some things like combinatorics and set theory where we get into this, but we never use it very well in engineering. So the idea is we take this, the complete design, and since we're doing top-down, we really don't know how it gets broken out yet. And the design process is how do we sort of break this out? How do we decompose it? So we want to do it so that and we'll know we get it right when if we add these things up, we get that one. And the other thing is we need them to be completely separate. So I use this mnemonic: collectively exhaustive, mutually exclusive, CME. And so as we work through the decomposition, we need to make sure that the decomposition is collectively exhaustive, mutually exclusive, and minimum number. So we need to make sure that the sum of the children in the decomposition exactly equals the parent. So we've done this like in free body diagrams. We get a force F, and we can decompose it into Fx, Fy, Fz. And that is a complete CME decomposition, collectively exhaustive. I've got all three components are orthogonal. Descartes got it right. Yep, that's it. That's space. And then, so collectively exhaustive, mutually exclusive. They're all at right angles, right? So Fy can change, doesn't have any impact on Fx. Right? So there it is. Sum of the children equals the parent. All right, quick example here. Saint-Gobain wanted a jig grinder, and they didn't want to get the expensive one. So jig grinding is used for making round holes in hard materials. So you get a little abrasive stick, and you spin it very fast, and then you move it up and down so you don't wear the stick out in just one position. You can buy these jig grinders. They're kind of expensive. And Saint-Gobain said, well, can we get one on a Haas mini mill? And those of you who've been over in our manufacturing labs know that we've got some of these. These are like a $30,000 item, unbelievably cheap. And while you don't necessarily want to do grinding in that because the abrasives will start messing up the ways, it turns out the thing is very accurate, and when you start losing some accuracy because the abrasive got in the ways, you can replace the whole machine and still be ahead. But what you need is that attachment. What I want to show you here, this is a student project, and it was a summer project for a couple students. And so here, this is the decomposition. We went through this, and you do lots of levels. When we were working on the orbital space plane, we had 2,000 FRDP pairs, and we're looking at the coupling. And so you get some software so you can collapse these things, just look at the high level, just concentrate on one branch. So that works real well. One of the things, too, that you do when you come up with your solid model on these designs is you put, oh, this is 5.2 in the decomposition. So I can go back to the decomposition. I can find out what this thing is for. You know, probably you've all done design reviews. You're looking at this thing and you're asking the designer, what does this thing do? What's that for? Why did you put that there? Right? And so here it is, all communicated. And sometimes I know when I do design, if I don't carefully keep track of that, I'm looking at it like 3 weeks later thinking, what did I do that for? So if you first do the decomposition, like I was showing you, put the matrices together, and then it should always be evident. One of the neat things, too, we're so lucky to have the nice facilities over there. The students machined all their parts and made that, and then Saint-Gobain used it. And that was just the first trial. Obviously, we weren't going to have those tubes all over. It needed a special high-speed spindle. And all right. So we talked about the change before. And so change, why is calculus so important? Well, it's about change. Okay, axiom 1 is about adapting to change. Axiom 2 is about robustness. All right, let's take a look. I said you could use, this is my last example, and we're just about out of time. So we said we could use axiomatic design to look at any kind of problem. All right, so designing a vacation. So what might you like on your vacation? Relaxation, romance. All right, so how might I get that? Well, I can try that out. All right, is this a good design? Well, if I take a look, yeah, so it shows the ethanol for the relaxation. However, does it have an impact on the romance? I'm afraid it might. Right? And so then, so in principle, well, first I'll adjust the relaxation with the romance, and then I should be able to compensate with the dancing. But we know that doesn't work very well. So this is not a good solution, right? Too much alcohol, the dancing doesn't work either. So there are some situations where we have to recognize that no amount of dancing could correct, for the overuse of ethanol. So what does this mean? We need to find a different DP, right, instead of ethanol. And so what else might we try? Yoga for relaxation. Right? And now, whoops, and this sort of slipped off the screen. So, yeah, we can see this now. All right. So now we've got a diagonal matrix. That's what we wanted. Right? So no interference, complete independence. So no surprise. We knew that ethanol was not a good solution to problems. And so yoga would be much better. So we need to select the DPs, and that's an example of how at the upper level you can choose appropriate DPs. Okay, and then let me go back to this projection. Okay, so one of the things we can think about too, designing the design process, right? Engineer, design your own design process. And I didn't talk much about that, but there's the possibilities. Thanks to, actually, it's Safina Machine Tool Company, which is sponsoring a project on axiomatic design, and Aclaro, the ADSI that make this. There's an example of one of their matrices. That's the way they show it. So thank you very much for your attention.